All right, so let's chit-chat about that next page on question number 13. So when you look at the difference between inertial mass and gravitational mass. So if I've got this chunk of block and I want to figure out how much it weighs, one option, if I'm on Earth, I hook it up to a Newton scale, I get a reading 3.50 newtons. It's cool, right? It works because we're in a gravitational field, and we as a species have said, hey, here's how we're going to measure acceleration. We can measure that value, then we can take that 3.50 newtons or whatever it is, and we can divide that by 9.8 meters per second squared, and we can go, boom, there's our mass. Cool. We can do that on the moon. We could do that on any planet that has a gravitational field. Hook it up, measure that interaction with the gravitational field, divide it by the acceleration, there you go. Problem being is like if you're in a continuous state of free fall, you're in transit between the Earth and Mars, you're in deep, deep space. Newton scales don't do you any good, okay? They don't. So what we have to do is figure out a way to measure mass without the assistance of a gravitational field. So that was what I showed you all yesterday. When you took that spring and you measured it go back and forth. So one option is you look at 2 pi times the square root of m over k. So if we wanted to get an idea of that mass, we can sit there and make it oscillate back and forth, okay? We could use a spring, whatever, anything that's going to oscillate. So we could measure t, you knew the spring constant, we knew that value of k, boom, we solve for mass. There you go, okay? So this is what I'm looking for when you answer question number 13. Say, we're going to start with this equation, we know the spring constant, we take a stopwatch, we measure the period of the oscillation, we solve for mass, okay? Now, when you get to question number 14, you're in deep, deep space, you go to the storage equipment for all the labs, and you realize somebody forgot to pack the spring.
All right.
So, we still have to find the mass. So, what I'm looking for on this one is that I tell you you have a force sensor. Okay, you're all familiar with force sensors. You've used them, right? Okay. You have a meter stick. Oddly enough, you can measure distance. You got a stopwatch. You can measure time. Okay. So, what I'm looking for when you answer number 14 is this question. How could I use that equipment, the force sensor, the meter stick, the stopwatch, to determine the acceleration? Now, you want to be very specific on how you lay this out. So, let me give you a hint. You know, F equals ma. Oh, right, I have a force sensor. I can measure how much force I apply to the object. Oh, I can solve for acceleration. Okay? Now, the trick here is, how are you going to measure the acceleration? Because you don't have an accelerometer. But you're going to know force, so you have to find a way to measure the acceleration. But you have a meter stick, and you have a stopwatch. So what I'm looking for when you answer question number 14, and you all have done this before, you've done this. What equation can you use, both those old school kinematic equations? What old school kinematic equation can you use to determine the acceleration of the object? Now, when I tell you this, I tell you be specific about what you would measure and the equations you would use. So here's how you'd want to start off. Apply a known amount of force to the object. Then figure out how you can use the stopwatch and the meter stick to figure out the acceleration. And you're going to say, hey, I'm going to use that equation. B squared equals E naught squared plus 2AD, which I don't recommend, but that's the idea. And you would say, hey, I'm going to use this equation, and these are the assumptions that I'm going to make, and then I'm going to calculate the acceleration. And then I'm going to take this divided by this, or whatever you're going to do to get the mass. So basically, when you answer number 14, you're basically writing out the lab procedure. You can say, okay, Connor, here's a mass, here's a force sensor, here's a meter stick, here's a stopwatch. How are you going to use all of those things to get the mass of the object? So Vitor should be able to read your answer to number 14 and replicate your results. Okay? All right, so make that happen. So,
That makes sense. You're tall.
back in the day.
Whoa!
Okay, so now we're going to transition into a kind of a summary of all this good stuff. So the whole key of what's happening on this next question, when you get to questions 15, 16, and so on, imagine that instead of oscillating vertically, where you have to worry about UG, now we're going to oscillate horizontally, okay? So when you look at this equation of U max and K max, so the whole key to this is that this is just a horizontal motion. There's no gravity to worry about, okay, which makes these concepts a little bit simpler to deal with. So any us is just going to be 1/2 kx squared. So here's the leap of faith that you have to take, is that when this thing oscillates horizontally, when it's at its maximum elongation, when you were to find U max, that's when it's going to have its maximum amplitude. That's when it's going to be its farthest point from equilibrium. So when you talk about U max, don't flip out and go, oh, here's the new equation. No, it's not. It's just energy stored in the spring. But we're going to rewrite it, and we're going to write it as 1/2 K A squared. Now, you can only do that when you're at its maximum amplitude. Because when you're at that maximum amplitude, that's when it stopped and it's going to change direction. Okay? So when you have a maximum elongation, the only type of energy you're storing is U max, and instead of X, we're going to make it look fancy, and we're going to put A, because all A is your elongation. Okay? So don't look at that and go, oh, there's a whole new equation. No, it's just 1/2 kx squared, we're just going to put amplitude. Now, on the other side of that, you can talk about when you're going to have your maximum kinetic energy. Well, when are you going to have your maximum kinetic energy? When it's in the middle, right? Because therefore you're not storing any energy in the spring. So when you talk about your maximum kinetic energy, K max, that's going to be 1/2 mass times V max squared. That's when you have your maximum velocity, and that's what we talked about on those previous pages on how you calculate V max. So that's why I said a lot of stuff that we talked about before is now going to get rolled into one big idea. So energy has to be conserved. Okay, you all figured that out on the lab final at the end of right before Christmas. So total energy in the system, okay, that total energy is going to equal the sum of two things. It's going to be the energy in the spring plus the kinetic energy. So here's the cool thing about this. So we're going to look at two extremes. When you're at maximum amplitude, okay, we're at maximum amplitude, what's the value of your kinetic energy going to be? Zero. So at your maximum amplitude, your kinetic energy is going to equal to 0, and your energy is going to be 1/2 K amplitude squared. So if we ever want to measure the energy that's in a system, one option is that we watch this spring oscillate and we figure out, oh, we'll just measure how far it is at its maximum elongation. We plug that in there, bam, there's the total energy that's in the system. Okay, so that's one option to find the total energy in the system. Measure its maximum amplitude, you know your K value, plug it in because it's all going to be energy stored in the spring. Now, your other option is when you have maximum velocity. Well, when is it going to have maximum velocity? In the middle. So what's your us value going to be? So your maximum velocity, us, is going to equal 0 because it has no x value. You're at equilibrium. And then your energy here is going to be 1/2 m times the max squared. Now, here's the story. Visualize this. Which of those values do you think is going to be easier to measure? Your maximum amplitude or your velocity max in the middle? Amplitude, okay? It's going to be tough to measure your velocity because your velocity is continuously changing. So in terms of what you can physically measure, you can record the motion with your phones, put a little meter stick back behind it, run it back in slow motion and go, oh, at its maximum elongation, it stopped at that point. So this one, from a lab perspective, is the easiest one to measure because all you have to do is just measure that maximum amplitude. Now, any equation has to work under any circumstance. What if there's no amplitude? What's the total energy of the system?
0.
0. Oh, okay, cool. It's not moving. There's no amplitude. Guess what? There's no maximum. Now, because that's 1/2 Ka squared, if you double the amplitude, what's that going to do to the maximum energy in the system? Well, you can go up by a factor of 4. Okay, triple it, it goes up by a factor of 9. Louis,
So what's held at 0?
what do you mean?
It says, what equation can be used to determine the total energy of the system, and what value is it assumed to be 0?
Okay, so that's what I was just talking about. When you get to number 16, okay, so what equation can be used to determine the total energy in the system? So you're going to do this, so you're going to measure it when it's at that maximum amplitude, okay? So when this thing is out here like this, stretched as far as it's going to go, so when it's going to,
Is that it? Okay, it's as it's fully stretched?
yes,
Okay.
So should we write down E instead of
yeah,
S?
because you want to find the total energy of the system. So here's the cool thing about this. So at maximum elongation, your energy equals your 1/2 Ka squared. But when you're at maximum velocity, your energy equals 1/2 mv max squared. So the beauty of this is that you can set these two equal to each other and go 1/2 Ka squared equals 1/2 mv max squared. So then, knowing this, then you can calculate your maximum velocity. Because you can measure that amplitude, set these two equal to each other, know the mass, know the K, find your Vmax. Does that speak to you, Sam?
It's pretty deep.
Okay. All right. When you get to question number 18, okay, let me explain what we're looking for on number 18. So assuming there's friction with the block, drawing an energy time diagram for just the mechanical energy. So when you're talking about mechanical energy, that's going to be the sum of the energy in the spring and the kinetic energy, okay? So what you want to look at here is that the energy of the block, assuming that it starts at its largest amplitude. So because you're talking about specifically just the mechanical energy, by definition, that mechanical energy is the kinetic energy, not the energy stored in the spring. So mechanical energy is the magic phrase for, oh, let's talk about kinetic energy. So you've got a graph like this. You got energy on this axis, and you have time here. So imagine this. Imagine that I stretch this out like this, okay? And here's where we are at time 0. We're going to keep track of energy as a function of time. And it's just your kinetic energy. So when this thing is completely stretched out here like this, how much kinetic energy does it have? 0. So this is going to start at 0. So then what's it going to do?
Increase.
It's going to go up, and then it's going to come back down. Now, if this was a frictionless system,
Oh dear.
what would that graph do? Go back up to same height, right? And it would just go back and forth, back and forth, back and forth. But because there's friction, oddly enough, when I do this, demonstrate this pretty simply. If I do this, gee, what happens over a period of time? Okay, so what's going to happen to this graph, assuming that it oscillates at least a couple of times?
It'll become shorter.
Yeah, so it's going to go more and more like this. Really?
Sorry.
Really?
I had to throw the word in.
Down, down.
Oh dear. No, that's not how it went.
So there's your answer to number 18. Now, when you get to 19, here's the difference with 19. Assuming there's friction's block, draw an energy diagram for the system consisting of both the block and the spring. So in other words, we're talking about that sum energy of 1/2 kx squared plus 1/2 mv squared. So when are you going to have your maximum amount of energy?
At 0.
Times 0. As time goes by, what's going to happen to the total energy of that system?
Decreasing
Because where is that energy going?
to heat as
Yeah.
friction.
So on 19, it's just going to go something like that. Sorry, you have to draw on 19, not make it complicated.
Are you picky about your waves?
As long as it looks something like that.
Yeah, they don't need to be even, right?
What do you mean?
Like they're not even.
Height?
I don't know if you
What?
can see this. Never mind.
Bro, you're making that
Would that
way,
be linear?
way more.
I don't know. Mrs. Fair was really, what's it called?
Just because
Nitpicky?
Yes. Like my sign, like they needed to be even. I mean, I don't know.
Wait, are we-
Depends how big the
we don't
friction
have, like,
is.
Oh.
Is it
There's
linear?
not really like a value to that.
No, I think it's not. That looks like a
Thanks,
sweep.
bro.
Yeah, it's actually, because it's squared, it's going to be quadratic.
Oh, that makes sense.
That's a square can be.
Come on, blue toy. You should know this, man.
Wait, 16 it's K.
16? Yeah. No. Yeah, because velocity was 0. Should I pause this?
Now keep going.
Okay.
Right there.
They're worse than mine.
Okay, now,
Just keep it.
here, we're in the home stretch, okay? We're in the home stretch.
Yay!
So, this is starting a whole new problem, okay?
Oh.
It's a whole new problem. So what happened before, done, okay? This is a whole new problem. So, imagine so let me kind of show you how this data would be generated on the top of this next page. So you got a mass of 0.125 kilograms, you put it on a string or oscillate it, and this thing is going to go up and down. So this thing is going to go like this, okay? So what's happening is that down below you have what's typically called like a sonic ranger. What it does is that it sends out a series of sonic waves, and it would be down here, and it would bounce off the bottom of the spring. And then as that gets that data back, it's going to generate this position time graph, okay? So the reason that it doesn't start at 0 is because your source is below here, and that's why basically this thing is oscillating. If you look at that scale, it's oscillating between 0.40 all the way up to 1, okay? So this is why it doesn't start at 0. So like you would have this thing up above the ground, and you're shooting the sonic ranger, and that's why it doesn't start at 0, because you're below it, and this thing is oscillating like this, and this is this distance that below. So you got this graph, and it's going like this. And that's actually here at 0.5. Okay? So, there's a couple of things that you look at. So first off, this thing is oscillating. Basically, if you drew like a middle line across there, and you want to calculate like that amplitude, so if you drew a line across there through the middle, so that middle line is about at 0.7. So that means this amplitude up here is about 0.25, and that's 0.25. So that use that number, because that way everybody's using the same numbers later on. So what we're saying is that that amplitude is going to be 0.25. Okay? So you drew that line through the middle, and this is a little sketchy in terms of how you kind of got to guess this, and everybody kind of could have guessed different points. That's why I wanted because if that amplitude is different, that's going to screw up everything else further down the line. So that's why I said, let's just make it simple and make sure everybody is using 0.25 meters as that amplitude. Now, then, the next one, and hopefully this now makes sense, okay? So here's your velocity time graph, okay? So you got some action like this. So you're starting there at 0 meters per second. So if you look at what's happening, notice that here's your source for those sound waves. It started at the bottom because that's at its lowest point. Then it's going to go away, and in this system, they're defining up as being positive because your velocity, notice your velocity time graph starts at 0. And then it's going to go up, right? And then it's going to go back to 0. So notice that when that velocity time graph crosses 0 again, that's when that position time graph is at its next maximum. So you can figure this out and go, okay, well, let's look at this. Well, look, even if I just gave you the position time graph, if you came in here on that position time graph and you drew tangent lines, notice those tangent lines would have positive values. That's why you start off and you have positive velocity down here on this graph. And at that very beginning, on that position time graph, it's very subtle, but it's there. At the very beginning of that, if you were to draw a tangent line at time 0, that would be a horizontal line, which is why that velocity graph starts at 0. Okay? So you got to understand how these two graphs correlate with each other. Like, I couldn't have that top graph and have my velocity time graphs go to negative. It wouldn't match up. Okay? I can't have a position time graph showing positive tangent lines and positive velocities, and then my velocity time graph showing negative values. Okay? It just can't work. Okay? All right. So, because this thing is oscillating horizontally, what are your 3 types of energy you can have on question number 20?
Kinetic.
You can have kinetic, you can have us, and you can have So there you go. Now, when you get to 21, 21 is this long, big, drawn out, and this is directly from one of the free response questions from one of the AP exams. So this is why I kind of said, okay, let's just work through this. So on this one, basically what they're saying is that the total energy, and this is what we talked about, is the sum of 2 things, potential energy and kinetic energy. Potential energy is sketchy because of the fact that it's vertical, so then it has UG and it has us, so it isn't. That's the beauty of being like horizontal motion. If it's horizontal motion, you only have to worry about us. If it's vertical motion like this, then you have to worry about UG. So that's where it gets a little bit ugly. But basically what they're saying, the equilibrium point can be defined as being the point at which potential energy is 0, setting E total equal to the maximum kinetic energy, where V equals V max. Write an expression solving the E total for U. So basically, here's what you're going to do. So U is going to equal E total minus K. Okay, so that's the opening solvo. Okay, that's the opening solvo. At any point, U is going to equal the difference between the total energy and however much kinetic energy you have. Now, this should make sense. When you're stopped, at the end of the oscillations, how much kinetic energy do you have?
None.
None. So what is your total energy equal?
Potential.
Whatever your potential energy is. Or if you don't have any U,
Use the K's.
all your energy is kinetic. Okay? That's it. Right? So just don't get wrapped up in the equation. Think that through on the extremes. Now, the tricky part here is that you need to write this in terms of, they tell you that you're going to have a V max. So here's the deal. So you're going to rewrite this as U, and instead of putting E total, we're going to write that as 1/2 K, or excuse me, 1/2 M. I got my K screwed up.
E squared.
1/2 M V max squared minus however much kinetic energy that you have. Now, if you really wanted to get fancy, you could write that as 1/2 M V max squared minus 1/2 M V squared. Okay? Now again, here's the deal. It's got to be able to work under any circumstance. So this is any velocity, and this is specifically V max. So think this through. If this is the velocity at any point, well, if this velocity is the same as your V max, you're in the middle, how much U are you going to have? Zero, because it's all kinetic. So now, if you really wanted to get fancy, you could factor out a 1/2 M and write it as V max squared minus V squared, if you really wanted to get fancy. But here's the bigger idea. Is that however much potential energy you have is the difference between the total energy in the system and however much of that energy is existing as kinetic. So if you don't have any kinetic, it's all potential. Okay? If it's all, that's the main idea. Now, the next part of is where it gets a little bit weird. Okay? So this is where they give you this equation. Vt equals negative V max sine 2 pi tau. Can use to determine the velocity at any point, right? Taking the equation for kinetic energy, which we just found, insert the Vt. So here's what we're going to do on number 22. We're going to start with this, and we're going to have U equals 1/2 M V max squared minus 1/2 M. Now we're going to do this grand substitution. So we're going to take that negative V max sine 2 pi t over period and substitute that in for V, and then we're going to square it. Okay? So this is a substitution and squaring. So this becomes V max squared, and because it was negative V max, but it's squaring it, so we don't have to, that gets rid of that negative value. And then times sine squared 2 pi t over t. So all we did was take, and this is the equation that you all worked with before. So all we did is we took the how you calculate velocity, okay? Velocity itself is that V max sine 2 pi t over t. All we did was take that and substitute that in for V. That's all we did, okay? That's all we did. So don't flip out and go, oh, this is tough. It was a simple substitution, and then we squared it. Okay, that's all we did. Yes?
So you don't need to square the inside of the sign?
No, we did. That's what. But you don't square the 2 pi t over t. You just put just sine squared.
Oh, okay.
Okay.
Yeah.
It's just, that's all. The only thing you square is that sine squared. Okay. Now.
So.
What?
Sorry. Are you squaring that V max squared sine squared, or is that already squared?
No, the V max squared that V max will be squared, and then you're going to have sine squared.
Okay, and then you square that whole thing again?
No. We squared it to get to this point.
Okay, cool.
So that's already squared.
I got you.
So when you take that V max sine 2 pi and square it, this is what you get. Okay, so there's no, yeah, we squared it, but then this is what you end up with. Now, when you get to 23, now they're going to ask you to simplify it. So if you'll notice, what you have in common, what you can factor out is a 1/2 V max squared out of both of these. So if you do that, then on number 23, you get 1/2 M V max squared times 1 minus sine squared 2 pi t over t. So all I did was to get from that to that is factor out a 1/2 mv max squared. Okay, that's all I did. Okay, don't flip out and go, oh, that's different. No, all I factored out, it's an algebra 1 move. It just looks really, really fancy. Okay? Now, when you get to, now we're ready to take on 24, which is what this is the whole thing of what we've been trying to get to on 24. So, here's the deal. What you want to do is calculate and make sure you're in radian mode. You want to calculate the value of u at these different times. 1/4 t, half t, 3/4 t, and 1 second. Now, so let's just step back here for just a second. Okay, let's just step back. So go up to that initial position time graph. What's the value for t? If I just gave you that initial position time graph, what's the value of t? Is it a 1/2 second or is it 1 second?
1.
It's 1 second because that's how long it takes to return back to that point. So on this one, we know t is going to be conveniently 1 second. So now we have t. So then we're going to have little t, which in this case is going to be 0.255. Now, here's the question. Before you do any calculations on 24, you want to calculate u. Are some of your answers on 24 going to be 0?
Yes.
Yes. Okay? You're going to have situations where u is going to equal 0. Guess what's going to happen when u equals 0?
Equilibrium.
And that's when you're going to have your maximum
Velocity.
velocity. Okay? So, what you want to do here is notice on this graph, you need to find V max. So if you go to your velocity time graph, okay, notice that those velocities are just a little bit above 1.5. So you can either use 1.5. I use 1.6 because it's a little bit above that. So what I did, and just make sure everybody's cool so we're kind of getting the same answers, use a V max of 1.6 meters per second. Because if you look on those graphs, okay, it's just a little bit above 1.5, so that's why I use 1.6. So that's what's going to be that. You have the mass of 0.125 meters. So go through, calculate this, and what you should see is that you're going to get the same answer 3 times and another answer twice.
Wait, a mass of one, what?
The mass is 0.125 kilograms.
Okay.
And your V max is 1.6. So let's think this through. You have, and you make sure you plug in that sine squared. So when little t equals 0, you're taking sine squared of 0. Sine squared of 0 is what?
Do you find sine squared?
Sine squared of 0 is going to be 1.
Sine squared of 0 is 0.
Sine of 0?
I don't know.
I'm confused. How do I put in sine squared in here?
Yeah, that's
It's just literally you put in sine squared and then you.
But there's no sine squared button, is there?
But you have like an error. You can do like
Oh yeah, I know that now.
you can do
It's
the
a-
caret.
Picture of it.
It's I don't know if I can do that. See, look. Yeah, it doesn't work. Look.
Do we have to? Can we just do one calculation, or do we
Yeah, it
have to show
doesn't
them
work.
all?
You can just do one.
Can you guys sine square anything in your calculator?
Just go math, go math. Go to math.
Put
Just
the
do
sign
the
in
sign
parentheses.
and then square it.
Here, let's do this. Let's just make this simple,
Bro, look,
okay?
0
just
squared.
gotta square whatever.
You all can put numbers into calculators. This is going to get complicated. I will never make you do this on the test, okay? Let me give you a hint. At time 0, if you do this, you get 0.16 joules.
Times 0?
Yeah.
Okie dokie.
Which is also going to be the same value at some other points.
You can just do it like that?
Yeah.
Okay.
Wait, 0.16 joules is our max?
Yeah.
Ooh.
Just to save everybody some hassle.
Wait, so is that doing that, the sine squared like that, is that the same as just putting in like regular sine of 4 pi squared? You know?
I would think so.
Okay,
They
I'm
don't
sorry,
know.
I have not had math in like a year, so.
I promise you on the test, I'm not going to make you do anything this
Okay.
complicated.
Wait,
I'm excited for this.
Wait, what's the period?
Bro, what?
What's the
the period?
Oh yeah, it's just point.
It's from peak to peak, you know?
Oh, I know what a period.
What?
Like, is it 1 for all of them? Period?
Yeah, I think
What?
so.
Is a period 1 second for all of them?
Yes.
Hmm.
Hold on, I want to try that.
I got 1.6 joules. So did I.
You did?
Yeah.
Okay, good.
We are going really fast, I feel like. Seriously, I don't know.
Oh my god.
I would press.
Intricate graph.
Why is there not pi on this stupid calculator? Seriously, how can there not be pi?
Yeah.
I think you just do it after. Is what they said to do. Although I really don't know. That looks a little sus. Oh my. What'd you get on this again? Oh, look at it.
So you just raise it.
Yay! Oh.
What? Yeah.
Wavy.
How was Portugal? What's
Oh, I did that wrong. Save things.
What's up? Yeah.
You skipped out class? You need the lines, bro?
Yeah, but it was
He gave it to us. That's what I mean. No, those are actually just right there. Those ones are for 30.
Okay, start that up one more time.
Oops, I did stop it.
Oh, okay, all right, well, never mind. I guess we can. All right, Poppy, you've seen this.
I messed up.
Okay, so let's get through that last page. So on 25, here's you've got this potential energy. And what I did is they didn't tell you specifically how to set up the grid, but it's 0.16, so I just said, okay, here's 0.1, here's 0.2. So the whole key to this one is that you're sketching the potential energy object, okay, as a function of time, and it says explicitly label any intercepts, asymptotes, maximum and minima with numeric values as appropriate, which they like to put in on the AP exam because it makes them sound really smart. So basically, all they're asking you to do is set up the grid. Okay, what's your scale going to be? So here's the story. So at time 0, this is where all of this comes into one big idea. At time 0, one of two things is going to happen. Either you're not going to have any potential energy, or it's all going to be potential energy. What's it going to be?
Potential energy.
So that's going to start up here at that 0.16, right? Now, what you have to decide is that now, Morella, this is important in terms of how you make this fit on the graph, okay?
Oh yeah.
Okay? So you just can't randomly do this. You have to look at it in terms of, because of the fact they gave you that time scale. So what you want to look at, and again, this is potential energy. It's never going to go negative because it's a scalar quantity. It'll go to 0, but it won't go negative. So you're going to start up here at 0.16, okay? Then what you have to decide is when does that potential energy go to 0, then when does it go back to a maximum of 0.16? If you're not sure, look at that previous question that you just did on 24, okay? That's going to tell you what that graph's going to look like. So let me give you a hint. It's going to go something like this, okay, down to 0. But the trick is you have to figure out when it's going to go to 0 and when it's going to go back to 0.16, okay? Now, when you get to number 26, explain the correlation between the potential energy graph and the velocity time graph. So what you want to look at is, again, you want to reference that velocity time graph. So you're going to say, okay, hey, when the velocity time graph is at some point, the potential energy graph is at this point. Or when the velocity time graph is at here, the potential energy graph is there. Okay, so that's how you want to approach that. Now, when you get to question number 27, so 27, you got to go old school back to how we started this lab. You want to find the value of K. You know the mass, you know the period. You look at the graph, find the period, and you want to solve that for K. So if you do 27 right, that K value should be around 5. Okay? Now, when you get to question number 28, will the mass undergo maximum acceleration at the top, bottom, or in the middle? Explain in terms of net force, force from the spring, and gravitational force. So guess what? When you answer 28, which 3 things do you think you want to talk about? Net force, force from the spring, and gravitational force. Now, Sam.
What? Yeah.
Merry Christmas. Listen to what I'm going to ask you. Okay?
Yeah, I was going to say different.
No.
Okay.
Close.
Oh. Interesting.
As the mass falls, which sounds like a horrible physics soap opera, as the mass falls,
Yeah.
what happens to the gravitational force?
It gets smaller.
Oh my god.
What are you talking about? Oh, it stays the same.
As the mass falls,
Yeah, it stays the same. It doesn't get different.
Wait,
it doesn't,
I thought it.
it doesn't get different. Thank an English teacher tomorrow. It doesn't get different. How about it stays the same?
Maybe it's too
But
small.
as it stretches, what happens to the upward force from the spring?
Greater.
That increases
Yeah.
because the F equals Kx. So when you're at the top of the oscillation, you have the minimum amount of force from the,
Spring.
but but that's when you have like your biggest value for, or excuse me, your gravitational force is still there. As it falls, the force from the spring gets bigger. Okay? Now, when you get to question number 29, assuming that the net force is only a function of the spring, okay, and that's a huge assumption, determine the maximum acceleration of the mass. So let me give you a hint. Force net, right, is going to equal mass times the acceleration. True? Okay, we're just going to make this simple. Technically, there's gravity thrown in there, but we're just going to make it simple. So the force from the spring is going to be Kx. So we can write that as Kx equals ma. At this point, you're going to know the K value because you found it up above. You're going to know that maximum elongation, and that's going to be that 0.25 value from the position time graph, because that's going to be that maximum amplitude. So you're going to know your K value, you know this, you're going to know the mass, you're going to find the acceleration. So if all goes well on number 29, that maximum acceleration should be around 10 meters per second squared.
Number 29.
Yep. And then on 30, you're going to draw acceleration versus time. Okay? And let me give you a hint. On that acceleration time graph, you're going to start up here at about 10. So you're going to go from positive 10 to 0 to negative 10. Okay? So on number 10, or excuse me, on number 30, you're going to start the graph up here. So what I have here, so here's what to do tomorrow. The first two packets I already gave you, on this blue sheet, the beauty of it is this is all multiple choice. Okay? Now, that doesn't mean you don't have problems to work out. When you get to question number 4, there are 2 springs. Okay? 2 springs. I say again, 2 springs. Just keep that in mind. So tomorrow, all of this will be handed in as one big lab.